Hello. For my project, my original proposal was to build a trebuchet and then examine the Lagrangian mechanics of so said trebuchet. Instead, I have left out building it and focused solely on the mechanics and finding the equations of motion of the trebuchet. To partially deliver on my initial proposal, I created a model in SolidWorks of a trebuchet. The deliverable attached in this folder is the trebuchet model and also the faulty Maple document that I wrote after working through these equations to help in the calculations. So starting with some quick background information, the first trebuchet was created in Asia sometime in the 7th century. These were quite crude, having the projectile on one end and a counterweight on the other, and it resembled more of a catapult than what we know as a trebuchet, and could launch a projectile a few hundred meters. As time went on, advancements to the trebuchet did as well, and the next big advancement in the trebuchet saga was the addition of the hinged counterweight, which allowed more potential energy of the system to be utilized by the projectile. But then the smarties of the medieval era discovered that using a sling to launch the projectile vastly improved the range by extending the arm and allowing the projectile to have much greater exiting velocity by utilizing the kinetic energy of the arm to increase the kinetic energy of the projectile. However, back in those medieval days, they didn't actually have physics to solve this, so it was basically intuition and trial and error, because Isaac Newton was not born and there were no mechanics around. So before we get into solving these, I made a couple of assumptions to help with these calculations. I'm assuming the center beam has no mass and there is no friction between any pieces. So we are going to start off by looking at this seesaw model, and we're assuming that the projectile and the counterweight are both fixed. It kind of looks like a pendulum with two masses on each end. Since we're assuming there's no friction after the projectile is released, basically the counterweight would just infinitely go around because of the momentum. And so thinking about solving this, we only have one degree of freedom, which is theta. So to find the position of m1 and m2, noted by x1, x2, y1, y2, we have to put them in terms of theta. And to save time, I have already written everything down, so I'm just going to be scrolling down and walking through it. So in terms of theta, these are the coordinates of m1 and m2 throughout theta's lifetime. So in order to construct the Lagrangian, we need the kinetic energy. So we need to take the time derivative of our generalized coordinates in terms of theta to obtain the velocities of m1 and m2, which are noted by these time derivatives. And now with the kinetic energy of the system, these are just the time derivatives. To get to the kinetic energy, which is here, which is pretty long, unfortunately, the kinetic energy of the system is the time derivatives of the x and y coordinates of m1 and m2. So the second line here is basically that just expanded out. The third line, I used the trig identity, sine squared plus cosine squared is equal to 1, which gets rid of all that stuff and helps it simplify. And then this last step was basically just taking out theta dot to make it a little bit easier. So then going down, the potential energy of the system, which is U is equal to mgy, is the energy stored within m1 and m2 due to gravity. So to solve this, we just yet again consider m1 and m2 and plug in our y1 and y2 coordinates, which is given by this, and then aptly simplified. And then now with both the kinetic energy and the potential energy, we can construct the Lagrangian, L is equal to T minus U. So plugging in our kinetic energy over here minus the potential. To simplify it, I basically just got this negative out and then made it so it is T plus U. So now to solve for the equation of motion, we need to utilize the Euler-Lagrange equation. Since we put our coordinates in terms of theta, the only degree of freedom we have is theta, so this is the only Euler-Lagrangian equation required. So now, if we calculate our derivatives out here, these are the correct derivatives, we can obtain the equation of motion. So with this, we can solve numerically for theta of t if you have all of the initial conditions of the lengths, masses, initial angle. So this is basically the simplest model, the seesaw model. The next model we're going to be looking at on Maple, because it would take forever to write out everything, is our optimal trebuchet. So here is my sketch of our optimal trebuchet, and it differs from from our seesaw model, as we now have these two extra lengths, which are basically adding two more pivots of movement. In Euler-Lagrangian terms, that means that there are two more degrees of freedom. So now we have 3 degrees of freedom to solve for the equations of motion, theta, phi, and psi. And also, going over the sling length, basically, L3, allows the beam basically to come up and have a much smaller footprint, and then right before release, the moment of inertia is much less in the system, and the rotational energy of the system is much bigger than basically the extending length of this beam, and it really allows this sling to just carry it with a much larger velocity, and allowing the range to go substantially further than our seesaw model. And so we are not going to walk through the problem again. We are going to look through this on Maple. Similar to the technical difficulties I emailed you about, Maple seems to not work again. I've tried restarting this a couple times to no avail, and this, the untitled.mw is the file that contains it. So hopefully I can email you tomorrow a semi-working version. So with the derivations not working, we are going to push this aside and instead look at the SolidWorks model that I created of the trebuchet. So again, technical difficulties resulted in this. So I'm leaving out the applications of those Lagrangian equations. Instead, I built this earlier today. So this differs from both of the models we previously considered because it has wheels, as you can see. The wheels allow the system to basically move during the launch, and that extra forward motion allows the system to basically add extra energy to the projectile, adding more range to the trebuchet in general. Because when this massive counterweight falls like that, my L4, in terms of, I was speaking earlier, the counterweight length is a little bit short on this, but with that falling, it will basically be the counterweight is very massive compared to the very small little sling I kind of constructed over there. So that will add lots of stress and also in the real world, because in our little systems we did not consider any friction, any air resistance, anything. In the real world, it's very different. So basically, you know, during this motion, there is energy being lost to friction, you know, heat dispersion. Also, air resistance will greatly affect the range of the projectile. So that's, or I'll open up a different view. So, and also this has many supports to make sure, you know, it won't fall apart. To start to sum it all up, it was honestly an incredible experience to be able to study basically all the advancements of the trebuchet in the last 12 centuries. All of these significant advancements in the trebuchet design all occurred before math in general, calculus, and it was just basic medieval ingenuity that created a, you know, a weapon that was a force to be reckoned with even after gunpowder and gunpowder artillery were invented, just because of the massive power of this. So yeah, and nowadays in modern times, we can take mechanics and we can solve the equation of motion for these, going from, you know, this basic seesaw model to a much more advanced model with 3 degrees of motion. And it actually wasn't that bad, as Lagrangian equations much better than trying to solve this with Newtonian mechanics, which would have taken the rest of the year to try and solve. And it was nice to build this model to basically address all of the shortcomings of something being taken out of a vacuum, for example, like our optimal model with no friction, no air resistance, nothing, and addressing the shortcomings and obstacles you actually have to address when trying to actually build one, and the differences in efficiencies and ranges. So that is my project on trebuchets. I hope you enjoyed. Thank you.